One I had for Matt, he said he coded all of Pokemon Red. He coded all of it. What the hell? And he coded everything. So it will pop up. It's like, oh, you have this Pokemon. It's this level. It does this damage. It does these 4 moves. It was like, it was really easy. It was really fun. And I was like, how long did it take you? He was like, just 2 weeks. He was like, well, you know, technically speaking, he's like, those developers probably had years to do it. I was like, bro, chill.
I was like slightly flexing on you.
Yeah, legit. But lightly flex. That's our game right there. Yeah.
Oh, yeah. Well, what's your grab? Small 3 freaking things in the chat tonight. Roll the counts tomorrow. Yeah. Look, you don't like it. Oh, at work, I have this. At work, I have this one. At work, I have that one. That one's so much better. I'm gonna buy that one once I graduate.
That's it.
What's up? This is 441 Biomechanics.
Oh, wow. You're talking about we're not.
What's that?
Oh, no, we're talking about play back.
Okay. Yeah. Good. Looking forward to it.
And next week, Professor? Next week. That's it tomorrow? Tomorrow. I mean, tomorrow, yeah.
Well, I won't be here tomorrow, but next week. Yeah, I have office hours after this. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good, hanging in there. Almost Thanksgiving. We got about a week and a half to go, and then we're on fall retreat. And then hopefully you guys can relax a little bit over fall break, but I'll be grading your guys' midterms over that time. Okay. So hopefully everyone got my email today. So I posted the study guide for the midterm exam. And so that's on Canvas for you. And so I think I linked it directly in the email that I sent. So so definitely take a look at that. So format for this midterm is going to be very similar to the first midterm. And so you're going to have kind of short answer questions, problem solving questions, and the like. Okay. In terms of content, basically it's just going to be homework 4 and homework 5. Right. So we only had time to do 2 homework assignments since then. So that's going to be your study for the exam. Okay. Okay. And so the plan for today is we're going to finish up our lecture notes on inverse dynamics. And so I think we stopped in the middle of an example last time. And so we're going to finish up that example today. We're going to talk about a couple more points and then do one final example before wrapping up this section. Okay. And then after today's going to be the last day. Today's going to be the cutoff for the midterm exam. So after today, anything that we cover on Monday is not going to be on the midterm. So the midterm is only covering up to inverse dynamics. Okay. Any questions about anything before we get started for today? Yeah, I know a few of you have reached out to me with project topics and project groups. So thank you guys for that. So remember, if you don't have a group by Friday, I'm just going to start assigning people. And so I want you guys to kind of be in a group and kind of know what you're researching for the final project. I haven't had a chance to respond to everyone yet, and so, but I did kind of look very briefly over all the topics that you guys have emailed me with, and I think thankfully there's no overlap between them. And so even if I haven't gotten back to you yet with about your project topic, I think they're all good. Okay, so I'll go ahead and confirm that after the class today. It's just kind of been hectic the last couple of days, so I haven't really been on top of everything yet. Okay, so let's go ahead and pick up where we left off. And so the topic for today is inverse dynamics. Okay, same as the last 2 lectures. And so inverse dynamics is this process that we're going through where we're taking our body segments there, and we're going to assume that they're in motion, and we're computing the net forces and net moments at all the joints in the body. Okay. And remember, the way that we're doing this is that we're using our equations of motion, very similar to how we did in the statics case. The big difference here is that we have to consider motion, right? And so when we sum the forces, we sum the moments. They're no longer going to be equal to zero. They're going to be equal to the mass times the acceleration, or the moment of inertia times the angular acceleration, right? And so in other words, we're going to sum the forces in the x direction. That's going to be equal to max. Okay. Sum the forces in the y direction. This is equal to may. And we sum the moments. Okay. Usually what we like to do in these cases, so this is a little bit different than our statics case, we sum the moments around the center of mass, because what that then allows us to do is that it simplifies the right-hand side of the equation. So we just have the moment of inertia multiplied by the angular acceleration. Okay. Okay. And kind of importantly, kind of what we went over last time is that when we're plugging in values when we're plugging in expressions for the linear acceleration, right? So ax and ay here, that's the linear acceleration of the center of mass of the body segment. Okay. Okay. We often put these expressions in terms of the angular quantities, right? And so that's kind of what we did last time. So we had to do things like product rule, chain rule, in order to get expressions for these. Okay. Okay. All right, so that's where we kind of left off, and so let me go ahead and we're not going to run through the whole example again, but let me go ahead and draw the geometry for the example one more time, just so that you can kind of see. Okay, and so in this example, what we're doing is we're examining the dynamics of a squat. Right, and so we have three segments here. And so we're going to start at the bottom. And so this is our foot. Okay. The foot comes up. And then this segment here is our shank, or our lower leg. Okay. Then we have another segment here. This is the thigh. And then this last segment here, this represents our upper body. Okay. We're not modeling all the individual arms and legs and arms and neck and head. We're just kind of lumping the upper body into one, because we're most concerned with the lower body in this case. Okay. All right. And so what we've been doing is that for each of the joints in this figure. Okay. So down here we have the ankle joint. Here's the knee joint. And this one right here is the hip joint, right? And so what we wanted to do is we wanted to use our equations of motion to solve for the net forces and moments at these joints. Okay. So we were done with the ankle. That was the first thing we did. We did the knee. Okay. And so the last joint that we haven't covered yet is the hip joint. Okay. All right. And so to solve for the expression of the hip joint, we need to make a free body diagram of the thigh segment. Okay. All right. And so our thigh segment is connected to the knee joint at the bottom and the hip joint up top. Okay. And so from the knee joint, we have the opposite, reaction forces from what we computed before. Okay. And so we have Fx2, Fy2, okay, and T2. Okay. Remember the directions that we're choosing for this one, because we already solved for the knee joint forces from the previous segment from the shank, the directions that we choose for this one are in the opposite direction. Okay. And so remember, it doesn't really matter what the first time you write the joint forces in a free body diagram in this analysis, it doesn't really matter what direction you choose for them, because ultimately, if it goes in the opposite direction, you're going to solve for a negative anyway. It's just that when you're writing those same forces on the next segment, you want to make sure you choose the opposite directions. Okay. Okay. All right, and then we have the net forces and net moment at the hip joint. Okay, so that's Fy3, Fx3, and T3. Okay, so those are our three unknowns in this case because we already know everything from about the knee from when we did the free body diagram of the shank. Okay. All right, so of course, we need to know where the center of mass is, and so the center of mass is here. Okay. Oh, excuse me, this is R2. Okay. The total length of this segment here is L2. Okay. And then we're going to assume that we know the mass of this body segment and its moment of inertia with respect to the centroid. Okay. And then we have an additional force to consider here, which is the force of gravity. So that's M2G. Okay. Okay. So now that all the forces here are accounted for, so remember we're these figures here look a little bit different than our static cases because we're not yet considering any muscle forces. And so the muscle forces are actually considered in the next step when we do muscle force optimization. But for now, all we're concerned about is just the net forces and net moments at the joints. Okay. And so you're not going to see any moment forces in inverse dynamics. Those come in the next step. Okay. All right, so let's go ahead and sum the forces. And so if we sum the forces in the x direction, okay, Summing the forces in the x direction, we have Fx2 in the positive direction minus Fx3, okay? So this is equal to M2 A2x, right? Let's sum the forces in the y direction. And so in the y direction, we have Fy2 minus Fy3 minus M2g is equal to M2 A2y, okay? All right, and so then let's sum the moments around the center of mass, right? And so remember, we almost always are going to sum the moments around the center of mass, just so that we can avoid that extra correction term. Okay. Okay, and so from the center of mass here, we have a lot of contributions to this. And so we have kind of 3 contributions from the knee, and 3 contributions from the hip. Okay. Okay, so let's write out the contributions from the knee first, right? So these are all the forces here with label 2. Okay. And so first thing we have is we have the pure moment T2. So T2 is going in the counterclockwise direction. And so counterclockwise means positive in our right-hand rule. Okay. Then we have the contribution to the moment from Fx2. So we have Fx2, R2, sine of theta 2. Okay. Oh, I should say that this angle right here is theta 2. Okay. So theta 2 is the angle that the thigh makes the horizontal. Okay. All right, and then we're going to subtract Fy2, R2, cosine of theta 2. Okay. So those are all the contributions from the knee, and the signs are appropriate based on kind of the direction of the moment that it induces. Okay. Then we have all the contributions from the hip. This is minus T3 plus Fx3 L2 minus R2 sine of theta 2 minus Fy3 L2 minus R2 cosine of theta 2. And it's all equal to I alpha 2. Okay. All right, so let's go ahead and put a box around these. All right, so these expressions look scary, but just like any kind of free body diagram, just take it kind of one term at a time. For every force, every moment that you have, think about what contribution or where is that contribution going in terms of the equations. Okay. All right, and so of course, these expressions aren't quite complete because what we have here are linear accelerations. Okay. So we have A2x and A2y. So we're not directly computing these, and so this is not something that's that we're measuring in our inverse kinematics, but we can compute them, or we can compute expressions for them using derivatives, like we mentioned before. Okay. All right. Before we do that, are there any questions on these equations here? How we got here? Okay. Okay, and so let's go ahead and solve for expressions for A2x and A2y. And all these are in terms of the angular kinematics, because that's the information, that's the data that we have. Okay. So let's start with x. Okay, so I think we did this one at the end of class last time, but we can go ahead and do it one more time. Okay. All right, and so the x position of the center of mass of the thigh segment is a combination of two terms, right? And so remember, in this problem, we're assuming that our origin, or kind of the 0, 0 point of our Cartesian system is at the foot, right? And so this x2 is the horizontal position of the thigh relative to the foot, okay? Okay. So you should always kind of be aware of where your origin is and make sure you're kind of consistent in that, okay? It doesn't matter all too much where you put your origin, and so you're definitely free to choose wherever you want for your origin, as long as you kind of stay consistent with that through every part of the problem, okay? And so from the first part of this problem that we started on Monday, we kind of decided that the foot was going to be our origin, and so we need to kind of stay consistent with that, okay? Okay, and so this position here, this is going to be L1 cosine theta 1 plus R2 cosine theta 2. Okay, because first we have to kind of travel up the shank, and then we travel part way up the thigh, and so that's L1 cosine. That's the part for the shank, and then R2 cosine theta 2. That's traveling upwards the thigh. Okay, all right. And so let's go ahead and take the derivative of this. And so taking the derivative will give us the velocity, that linear velocity. Okay. And so it's going to be minus L1 omega 1 sine of theta 1 minus R2 omega 2 sine of theta 2. Okay. We can take one more derivative, and so one more derivative here is going to split both of these terms because they both have a time-dependent term, and so we need to use product rule here. Okay, so it's going to be minus L1 alpha 1 sine of theta 1 minus L1 omega 1 squared cosine of theta 1. Okay, minus R2 alpha 2 sine of theta 2 minus R2 omega 2 squared cosine theta 2. Okay. Again, it's a lot of terms, but just kind of take it kind of step by step. Okay. All right. So now that we have this expression for a2x, we can plug it into this expression up here, not for y, for x. Okay. And so that'll complete that equation. And so on the left-hand side of the equation, we just have x2, x3, and then we have the mass times the linear acceleration. Okay. Okay, so let's do the same thing for the vertical, vertical position. Okay. And so our y2 in this case is going to be L1 sine of theta 1 plus R2 sine of theta 2. Okay. We take one derivative, we're going to end up with Vy2, and so this is going to be L1 omega 1 cosine theta 1 plus R2 omega 2 cosine theta 2. We take one more derivative, that's going to give us the acceleration. So that's L1 alpha 1 cosine of theta 1 minus L1 omega 1 squared sine of theta 1 plus R2 alpha 2 cosine theta 2 minus R2 omega 2 squared sine of theta 2. And similarly, we would plug this in for AY up above, okay? Okay. And so what's important about these acceleration expressions here, there's a lot of terms, a lot of unknowns, but let's look at all the terms that we have. So we have lengths, so we have L1, R1. So theoretically, those are relatively easy to measure, and so those are known. Okay. We have angular positions, angular velocities, and angular accelerations, right? So that's the theta, omegas, and the alphas. Remember, all of those are known because we're doing this analysis after doing a motion capture study, after doing a human motion kinematics, okay? And so, even though these are very long equations here, essentially they're just going to boil down to a number, because once we kind of plug in all the data that we know, this just becomes a number, okay? Okay. And so the accelerations are all known, okay? What's unknown in these expressions up here, we have to kind of come back all the way up, are all of the forces and moments at the hip joint. So that's anything with 3. So we have fx3, fy3, t3, fx3, and fy3. Okay. But everything else is known, right? So all the 2 quantities, fx2, fy2, t2, those we found out in the previous step. Okay. And so these 3 equations here can be solved for these 3 unknowns. Okay. And so in theory, if you had numbers for these, you could plug them in, and those would be the only unknowns in your equations. Okay. It would be very tedious to plug it in. And in fact, the second example that we're going to do today, we're going to use MATLAB to plug in the numbers for us, just because it's otherwise kind of a little bit too tedious to do on our own. But as long as you have these expressions, you can always kind of plug in the data that you have. Okay. All right. Any questions on this example here before we move on? Yeah.
On the exam, are we gonna have to plug in everything to get a number?
No. So for the exam, I'm going to have you guys just derive these expressions here, and so this is kind of what I'm looking for. And so yeah, because at that point, plugging in is just kind of just busy work and almost kind of a waste of time on an exam. So yeah, I'm mostly just looking for these. Okay. All right. Okay. So let's take a step back, and so let's kind of look back at this example again, and let's kind of think about how we started the example, and think about, are there any other ways to approach it? Okay. And so if you remember from last time, the where we started the example was at the bottom, right? And so we started with the ankle by making a free body diagram of the foot. Okay. Okay. And there's a couple of reasons why we did this. One which is certainly convenient, but not necessary. But the other part is one that's kind of more important. Okay. And so the first reason, which is kind of more just a convenience thing, the foot we assumed is stationary. Okay. Right. And so AX is equal to AY is equal to alpha is equal to 0. Okay, so we have no motion, and so there's no acceleration, no angular acceleration, velocities, or any of that. Okay, and so that made things a little bit easier because in our equations of motion, we didn't have to take derivatives to get the accelerations or anything like that. Okay, so that was kind of nice, but not required. And so technically speaking, you can start from a place that's not stationary, and still do the analysis. Okay, the other point that we didn't really talk about last time was the fact that this is where our external force was being applied, right? And so if you remember from from last time, what we said was that we had some kind of a force that's being applied on the ankle, okay? Right, and so that was the normal force that the ground is exerting on the person as they're doing their squat, right? And so, the main reason why we started the foot is that this is where our external force is applied. And actually, this is the this is the property here. This is the attribute that's going to end up being kind of more important. Okay, because when you start to do these problems on your own, right? And so and you'll see this when we do another example, right? The question kind of always becomes in terms of where do you start, right? And so writing out the free body diagrams and doing the equations of motion and all that stuff, I think this is hopefully everyone should get enough practice with that. But kind of the bigger kind of question that you should be asking yourself is, where do I start my analysis? Right? And so generally speaking, if you want to have kind of a little bit of an easier time in terms of in terms of application, it's always good to start where you have an external force being applied. Okay. And so you should start making your free body diagrams there. Okay. And the reason for this is that it basically kind of allows you to solve the problem kind of step by step. Okay. And this is what I mean by that. Because if you start your analysis from the location where the external force is applied, what that does is that it allows you to compute explicitly the net joint forces and net joint moment at the joint that's kind of immediately by it. Okay. And so let's recall. And so, let me go ahead and draw my foot here. Okay. That's a foot. I know it's a triangle, but use your imagination and imagine it's a foot. Okay. And so what was unique about starting here was that, we had the external force. So that was good. Okay. And we only had one joint that's in this free body diagram, right? And so we had, let's see, Fx 1, Fy 1, and like that, T1. Okay. So since Okay. And so since the foot is the most external segment, we only have one joint here, okay? And only having one joint means we only have 3 unknowns to solve for, okay? And so having only 3 unknowns is good because we know that when we write the equations of motion for the segment, we're going to get 3 equations of motion, right? So 3 equations of motion for 3 unknowns. We'll be able to solve for these unknowns kind of right away, okay? Before considering any other segments. Okay. Because that's good because when we move on to the next body segment, right? We're gonna have expressions. We're gonna assume that everything at the ankle was known because we solved for it in the previous step. Okay. So generally, this is kind of the approach that's recommended, just that you kind of solve every joint kind of sequentially one by one. Okay. Technically speaking, you don't have to do this, and so you could start from the other end and kind of work your way back. It's just that for every segment that you cover up to that point, you're going to have 6 unknowns and only 3 equations. Because if you have 2 joints connected to your segment, right, that's 2 sets of net joint forces and net joint moments that you have to solve for, right? Eventually, if you kind of work your way through the entire problem, you're going to get enough equations to solve for the unknowns. It's just that at that point, you're working back from 9 equations, right? So you start from the 7th, 8th, and 9th equation. You solve for those. You go back to the 4th, 5th, and 6th equations. You solve those. You go back to the 1st, 2nd, 3rd. So that's definitely possible. So you can definitely do that. It's just that this I think makes it a little bit easier and a little bit easier for you to kind of check your results. Okay. And so that's kind of usually the recommendations to start at the point where you have an external force, because that's likely going to be some external body segment with only one joint. Okay. All right. And so with that in mind, we can actually come up with another alternative way to solve for this problem. Okay. Because if you notice, all throughout this example, we actually never made use of the upper body segment, right? It's there, but we actually didn't need a free body diagram here because we got everything we needed from the foot, the shank, and the thigh, right? Oops. But an alternative way to solve this problem is you can actually go from the upper body and go down, right? Because what do we have here, right? In this ball right here that we have at the end of the upper body segment, this represents the mass. This represents the mass of the entire, or the weight of the entire upper body. Okay. And so even though technically that's an internal force, right? So the mass and the weight of the entire body is internal to the body, okay? When you're just considering the legs, this technically counts as an external force, right? Because it's it's not something that we're considering here, okay? Okay. And so another way to approach this problem is that instead of using the normal force from the ground, we can instead start from the top, measure the overall mass, the overall weight of the upper body, okay? and then kind of work our way down. So we would do a free body diagram of the upper body segment. That's going to allow us to solve for the joint forces and joint moment at the hip. Okay. Then once we have that, then we move down to the thigh, solve for everything at the knee. And then finally, we end up with the shank. And then that'll allow us to solve for everything at the ankle. Okay. So that's definitely a valid way to do that as well. Okay. The only thing that you'd have to worry about, or the main thing you have to worry about, is computing the linear accelerations, right? Because if you start from the top down and you don't shift your origin, then the acceleration of the upper body is going to be quite a doozy to compute, just because you need kind of 3 terms to do that. Okay, so there's a lot of trade-offs and a lot of ways to kind of approach these problems. Lots of different kind of pathways that you can take, and so I want to make you aware of all the different pathways. In the end, as long as you're kind of consistent in all your equations and you plug everything in correctly, you're going to end up with the same answer. It's just that, maybe some pathways are kind of a little bit easier than others. Okay. So let me write one final note before we do our next example. So when starting, okay. And so when you start your analysis from a non-stationary point, okay, you want to be careful when you are computing the linear accelerations of that segment. And so you want to have care, so you want to kind of choose the location of your origin carefully. Okay. Because ideally, most of the time you want to choose your origin to be a fairly stationary point. You don't want your origin location moving with time. Okay. All right, and so even if you were to start that analysis from the upper body, I would probably still keep your origin at the foot, because that's going to be the most stationary point in the entire line. Okay. Right, because you definitely don't want to get into the realm of moving reference frames, and so especially accelerating reference frames. So then it's then you're really in trouble at that point. Getting like non-inertial frames and stuff like that. Okay, any questions on this before we do our final example here? Okay, all right, so let's do one more example, a fresh example here, so you can kind of see how this all works out from the beginning to the end again. Okay, and so let's do the inverse dynamics of a dumbbell curl. Okay. All right, so we're gonna have 2 segments here. Okay, and so we're going to start from the top here. So here is the shoulder. Okay, the shoulder is going to be our origin, so that's going to be the most stationary point of this analysis here. Okay, so everything's going to be measured relative to the shoulder and going down, right? And so for the upper arm, okay, the upper arm we're going to say has a mass M2 as a moment of inertia of I2. Okay. Relative to the shoulder, the center of mass of the upper arm is going to be given by R2. Okay. The total length of the upper arm is going to be given by L2. Okay. Next, we have the lower arm, and so the lower arm is going to have an angle θ1. It's going to have its mass here. Okay. The mass is going to be measured relative to the elbow joint. It's going to have a a distance R1, and the total length of the lower arm is going to be given by L1. Okay. And then at the very end of the diagram here, we have the external force that's applied by the dumbbell. So we'll call that FW. Okay. Okay. And so in this case, we're not going to consider the wrist joint. So we're going to assume that the hand is relatively rigid. Okay, just to save ourselves a little bit of time. Okay. All right, and so in this problem, I am going to give you some numbers. Okay. All right, so these are relatively consistent with a normal person. Okay, so assume M1 is 1.37 kilograms, I1 is equal to 0.0084 kilogram meter square. Okay, R1 is 0.13 meters, and L1 is 0.2718 meters. Okay, that's for the lower arm. For the upper arm, we have the following parameters. We have M2 is equal to 2.37 kilograms. I2 is equal to 0.0175 kilogram meter square. R2, as shown in the figure, this is 0.1511 meters, and L2 is 0.2977 meters. Okay. Okay. So we're not going to plug these numbers in until the very end, but but at least you have something to kind of plug in here, and you'll be able to get some good some good data from this. Okay. We do, yes. So that's going to be the next part. Yeah, we actually have values for theta and the omegas and the alphas as well. So the angular positions, velocities, and accelerations.
Or it's 2.37.
Yeah, 2.37. Yeah. Okay. So those are all of our parameter values, and so you can see that it very quickly it kind of gets out of hand. Okay. And so the other thing that we're given here is we're actually given the the kinematics. Okay. And so we have six quantities here. So we have omega-1 or theta-1, omega-1, and alpha-1. So these are the angular kinematics of the elbow joint. Okay. And we have theta-2, omega-2, and alpha-2. And since this is a dynamics problem, all of these guys are going to change with time. Okay. Should give myself more room on the left-hand side. Okay. And so this first column here is going to be time. And so it's going to be 1. We have 5 data entries here. So 1, 2, 3, 4, 5. Okay. 5. All right, and so we're going to assume that there's maybe, maybe a tenth of a second in between each of these measurements. Okay. Okay, so for theta one, for a dumbbell curl, you can start low and you kind of curl up towards your body. Okay. And so the measurements for this are going to be, we're going to start at 5 pi over 3 for theta 1, then 16 pi over 3. Okay. Then we're going to get down to 0. All right, question. So do we consider the instantaneous values for solving these problems? Yes, you do. Yeah, so all the equations that we're solving for, those are the instantaneous values for each of the, angular kinematics, so theta, omega, alpha, right? And so what you're going to see is that, what we're going to get at the end, we're going to ultimately solve for, the net forces and moments at the elbow and the shoulder. And so we're going to present it as a data table, just like this as well. So we'll get a measurement for Fx, Fy, and T at the first time instance, and then the second, the third, and the fourth and the fifth time. Okay, so those are all the measurements for theta 1. So all these are given in radians. Okay. So the equations that we have work for both radians and degrees. It's just like normally with these things, you just have to be consistent with it. Okay. So for omega 1 here, at the first time point, it's going to be 100 radians per second. Okay. Second time point is going to be 200 radians per second. Okay. Then 150 radians per second, 125 radians per second, and 0. Okay. For alpha 1 here, alpha 1 is going to be 500 radians per second squared. Okay. That's going to be true for the first two time points here. Okay. And then we're going to start to decelerate. And so we have minus 250. Radians per second squared, minus 125 radians per second squared. Okay. And then minus 625 radians per second squared. Okay. Okay. And so we're going to assume that this person has very good form for their bicep curl. So they're not going to involve their shoulder at all. So the shoulder is going to be actually mostly stationary in this case. Okay. The only quantity here that's going to be non-zero is going to be theta 2. And so theta 2 here is going to be 5 pi over 3 at all instants in time. Okay. And then the angular velocity and angular accelerations for the shoulder joint are all going to be 0. Okay. And so in this case, we have one joint that's in motion, right? So our elbow joint experiences a lot of motion as we go through the dumbbell curl, but the shoulder is going to be relatively stationary. So we're going to keep that one still the whole time. Okay. Okay. And so considering all of this data, so all of the kinematics and all of the measurements on the arms, we're going to compute. Let's compute the net joint forces and net moments of the elbow and shoulder joint. Okay. All right. Any questions on the setup for the problem? Okay. So it's a lot of data, but don't worry. It's what we're going to do here is we're going to solve for the expressions. So we're going to come up with equations for our net joint forces and moments, and then we're going to let MATLAB kind of plug it in for us. Okay. Okay. So we have two main segments here. So we have both the lower arm and the upper arm. Okay, and so we can kind of choose to start our analysis with either one. And so kind of what we kind of just mentioned before this example, In this case, the better segment to start with is going to be the lower arm. Okay. Because the lower arm here, we're not considering the wrist as a separate joint here. And so the lower arm is going to be where our external force is being applied, FW. Okay. And we only have one joint in this segment. Okay. So that's nice. And so because we only have one joint as part of the lower arm segment, we'll be able to solve for expressions for the X and Y forces at the elbow joint, as well as the net moment at the elbow joint as well. Okay. Okay, so let's go ahead and do that. So let's do the free body diagram of the lower arm. Okay. All right, so the free body diagram of the lower arm looks something like this. Okay. M2, or excuse me, M1, M1, I1. Okay. And so the force of the weight, which I don't know if I gave you. What is that weight force? I have it. It's in the code. It'll be in the MATLAB code that we show. Okay. So we have the external force from the weight, FW. We have the force of gravity, that's M1G. Okay. And then we have all the joint forces at the elbow. So we have FY1, FX1, and then we have going the other direction. Sorry. And so we have T1 going in a clockwise direction. Okay. What I wanted to draw here was the angle, theta 1. Okay. All right, so that's our free body diagram. So let's go ahead and write our equations of motion. Okay. So let's sum the forces in the x direction. And so in the x direction, we actually only have one force. And so that's going to be minus Fx1. Okay. That's going to be equal to the mass multiplied by the acceleration, Ax1. Okay. Let's sum the forces in the y direction. And so in the y direction, we have a minus Fy1. Okay. Minus M1G minus Fw. Okay, this is equal to M1 AY1. Okay. And then if we sum the moments, we're going to sum the moments around the center of mass like we normally do. Okay. We have a minus T1, that's our pure moment. We have a minus Fw. Okay. Oh, it would help to have the geometric dimensions too. And so remember, everything here is measured relative to the elbow in this case. And so the location of the center of mass, that's going to be R1. Okay. And then the total length of the entire segment here is L1. Okay. All of that measured relative to the elbow. Okay. Okay. And so the moment from the weight here is going to be minus Fw times L1 minus R1 cosine of theta 1 plus Fy1 times R1 cosine of theta 1 plus Fx1 R1 sine of theta 1. Okay. And all this is equal to I times alpha 1. Okay. So this is good. So the moment equation is actually ready, and so we can use that equation kind of straight up as it is. Okay. What we don't have ready yet is the force equations, because we need to come up with expressions for AX1 and AY1. Okay. Okay. And so for these, just like before, we're going to start with the positions, y x of t and y of t. Okay. And then we're going to take our derivatives in order to plug in for these. Okay. Okay, so this one's a little bit different than our previous one, because in our previous example, our starting body segment was also the stationary one. Okay. Here we're starting from a point where the stationary joint is kind of on the other side. Okay. And so our position here relative to the origin for this segment is going to be L2 cosine theta 2 plus R1 cosine theta 1. Okay. That's the x position. And the y position, we have L2 sine of theta 2 plus R1 sine of theta 1. Okay. Let's go ahead and start taking derivatives. And so Vx of t, this is equal to minus L2 omega 2 sine theta 2 minus R1 omega 1 sine of theta 1. Okay. And then the acceleration is one more derivative off of this. And so this is going to be a minus L2 alpha 2 sine of theta 2 minus. Okay. Explain again why we use L2 and R1. Yeah, for sure. And so, to kind of see that, we have to kind of go back to our original diagram here. Okay. And so in this case, if you look at kind of how everything is measured in this diagram here, everything is basically measured from the shoulder, right? So our shoulder here, this is our stationary point. Okay. The stationary point being our origin, right? And so when we want to measure, or when we want to kind of quantify the x position and y position of the center of mass of any point in this diagram here, it's going to be relative to that stationary point. So it's going to be relative to that origin. Okay. And so the only measurements we're given here are the measurements along the arm. So those are the ones we have to rely on in terms of locating our point here. Right. And so when we want to state the x position of the lower arm here, we have to kind of travel down the upper arm first. So that's going to be L2 cosine of theta 2, and then R1 cosine of theta 1. Yeah. And so it's kind of a function of the fact that our origin is kind of on the other segment. So we have to kind of add additional terms. Does that answer your question? Awesome. Cool. Okay. Where were we? Okay, still taking derivatives. And so we have a minus L2 alpha 2 sine theta 2, and then minus L2 omega 2 squared cosine of theta 2. Okay. Then we have a minus R1 alpha 1 sine of theta 1. And then a minus R1 omega 1 squared cosine of theta 1. Okay. All right. And so let's do the same thing in the y direction. So for Vy of t, we're going to take one derivative here. So it's going to be L2 omega 2 cosine theta 2 plus R1 omega 1 cosine theta 1. Okay. Let's take one more derivative in y. And so we're taking one more derivative in y. We have an L2 alpha 2 cosine theta 2 minus L2 omega 2 squared sine theta 2. Okay. Plus R1 alpha 1 cosine theta 1 minus R1 omega 1 squared sine of theta 1. Okay. Okay. And so, of course, the next step here is just to plug them into the equations of motion. Okay. So plug in for AX and AY. Right? So I'm going to say plug in to equations of motion. Okay. So I'll leave that up to you guys. And so at that point, it's just kind of a lot of writing, but you can tell that, you know, it kind of makes our solutions here a lot longer. Okay. And ultimately, remember what we're solving for here is the forces, right? So Fx1, Fy1, right? After we plug in for Ax and Ay, we're going to be able to solve for Fx1, Fy1, just because everything in the acceleration is known, right? And so that was given to us in the problem. In terms of a lot of kind of almost like an obnoxious amount of numbers, okay? And then once we solve for Fx1, Fy1, we'll be able to plug those into the second equation and solve for T1, okay? And so since we started with the lower arm section, right, even though it was a little bit annoying to compute the linear accelerations, we have 3 equations and 3 unknowns, and we can solve for all 3 of our knowns exactly. Okay, so that's good. So that's half the problem already. So half the problem is, you know, solve for everything at the elbow. That's what we've done, right? So these 3 equations here will give us the expressions for the elbow. Okay. Okay. Of course, you know, if you actually wanted to compute the numbers for this, you have everything that you need. Okay, so you can plug in all the numbers from the beginning. But I think that the better way to do this is going to be through MATLAB. Okay, and I'll show you how to do that in a second. All right. So the MATLAB, of course, is optional, and so you know I'm not requiring you guys to know MATLAB for this course. But you know, for situations like this where you have a lot of equations and a lot of terms, you know, MATLAB often makes it very simple and kind of very systematic in terms of how it applies these things. Because if you're plugging this in by hand, it's a lot easier to kind of make a mistake. Okay, and so I'm going to show you the MATLAB script. You know, not really expecting you guys, you know, or not really, you know, expecting you guys to learn or to use it. But just show you as a way, or kind of the more practical way to kind of churn through a lot of these equations here. Okay, so now that we're done with the lower arm, so let's go ahead and work on the upper arm. Okay, so we're going to start with a free body diagram once again. Okay, I'm going to go fairly quickly here just to make sure that we can kind of get through everything. Okay, so for the upper arm, we're connected to 2 joints here. So we're connected to the elbow joint at the bottom and then the shoulder joint at the top. So we're going to have two sets of joint unknowns here. Okay. Okay, so our upper arm in this case looks something like this. Okay, we have our center of mass here. So that's going to be M2, I2. Okay, we have the force of gravity, M2G. Okay. All right, and so we have the first thing we're going to have is the elbow joint forces, and so this is going to be Fx1, Fy1, and T1. Okay. So all 3 of those are known, right? So Fx1, Fy1, T1, we just solved for their expressions in the previous part. Okay, so everything down here is known. Okay. What's unknown is going to be the forces at the top. And so let me use red for them to kind of highlight it. So we have Fy2, Fx2, and T2. Okay. And then just like before, everything is being measured relative to the shoulder joints. So we have R2 and L2. Okay. Okay, so let's go ahead and write out our equations of motion. So we have sum of forces in the x direction. Okay, so we have 2 x forces here. So we have Fx1 minus Fx2. This is equal to MAX2. Okay, Some of the forces in the y direction, we have Fy1 minus Fy2 minus M2G. So this is equal to M2AY2. Okay. And then we have the sum of the moments around the center of mass. Okay. All right. So just going really quickly here. First, we have our pure moments. And so our pure moments are T1 and T2, okay, with their respective sign convention, because one is clockwise, the other is counterclockwise. Okay? Or I should say T1 is counterclockwise and T2 is clockwise. And so that's why we put the signs like that. Okay. Then we have the contributions from the joint forces. And so we have plus Fy2, R2, cosine theta 2, plus Fx2, R2, sine of theta 2, okay, plus Fy1, L2 minus R2, cosine theta 2, plus Fx1 times L2 minus R2, sine of theta 2, okay? And all this is equal to the moment of inertia, I2, multiplied by the angular acceleration, alpha 2. Okay. All right, so let's go ahead and box these. Last thing that we need here is just the linear acceleration, so ax2, ay2. So let's go ahead and solve for those expressions. These ones are actually going to be simpler just because the our origin is right there, right? So our origin is at the shoulder, and so our accelerations here are going to be a lot shorter. Okay, so let's start with x2. Okay, x2 in this case is just r2 cosine theta 2. Okay, we take one derivative, we get minus r2 omega 2 sine of theta 2. Okay, we take one more derivative, we get minus r2 alpha 2 sine of theta 2 minus r2 omega 2 squared cosine theta 2. Okay, then we have y2, that's r2 sine of theta 2. Vy2 is r2 omega 2 cosine theta 2. And then ay2 is r2 alpha 2 cosine theta 2 minus r2 omega 2 squared sine of theta 2. Okay. I know I'm going really fast, but I want to make sure that we get to the math. Okay. Question? All right, so all of these things together, and so you can plug all of these in, and then get this kind of gargantuan expression, okay? And then eventually you'll be able to solve it for fx2, fy2, and t2, okay? It looks like a mess, but the vast majority of these are known, because these are data that we're given. Okay. And so the next step here is of course actually plugging into these equations. And so we're given the time-dependent data as part of the problem. And so, like I mentioned, a couple of ways that you can do this is that you can actually, sit there and kind of plug into all these expressions for each point in time. You're certainly welcome to do that. But I think the more time-efficient way is to write a MATLAB script to do it. It's not a long MATLAB script. It basically just inputs all of these equations here. It has lines of code for all the data. And then just kind of outputs the result. Okay. All right. Any questions on this before we take a look at that? Yep.
On your equation of motion.
Mhm.
You have FY1 as positive, but on the FPD, it's going down.
That is a great point. That is a mistake.
But then another thing is that the FY2 is also pointing down. Shouldn't that be pointing-
Yeah. So the FY2, it doesn't matter too much, just because that's the first time we've seen FY2. And so we kind of have freedom to kind of choose the direction there. If we were to kind of continue this analysis, and so let's say that we were to make a free body diagram of the neck or something, that we have to make sure the FY2 is in the opposite direction. But good catch on FY1, because in the other part of the problem here, we had FY1 going down. That means when we moved up to the upper arm, we needed FY1 to go up. Yeah, so that was a good catch. Thanks for catching. All right, any other questions? Yes.
So every time we do a joint, like we take it to another segment and we've already calculated, we always do the opposite of it.
Exactly, right. Yeah. So it's the same magnitude, it's just opposite direction, because it's a separate body. Okay. All right, so very quickly, in 1 minute, let's look at the MATLAB code. I should have downloaded this beforehand. Oh, 3 new messages. Oh, never mind. Okay. Okay, so I'm going to do things in parallel. So I'm going to start MATLAB up. MATLAB is not on this computer. Great. Okay. Anyway, I'll show you the code on Canvas, and then unfortunately I won't be able to run it, but you can use your imaginary MATLAB compiler in your head, which is a little bit more difficult than the imaginary art in your head. But okay, and so if you go to the files here and you go to, oh, did I not upload it? There it is. Okay. Okay, so this file is available for you to download. Okay, and so you can see here that in this file here, I've set variables for all of the parameters, and so these are all the parameters that were given in the problem. And here we finally get the answer for the mystery weight, and so we're currently 65 here. That's not 65 pounds, it's 65 newtons, and so that's maybe about about 30 pounds, which is still kind of a lot, but but less than 65. Okay. You can see here that I have a section of code here to specify the kinematic data. So here's all the theta 1s, omega 1s, alpha 1s. And so you can see I've saved them as vectors. Okay. Same thing with theta 2, omega 2, and alpha 2. And so you can see for the most part, your shoulder joint is mostly, stationary. Okay. And then the last part of the code right here, you can see I've just directly input the equations for fx1, fy1, t1, and fx2, fy2, and t2. Okay, so these are just exactly as we derived in the code. And so even though I call this a MATLAB code, it's just kind of a glorified just calculator, kind of simplified for us. And if you run the code, then what you'll see printed to the console or printed to the workspace is the answers for fx1, fy1, t1, and fx2, fy2, t2. So unfortunately, I can't run the code, so I can't show you the answer, but it's available for you online to see for yourself. Okay. All right. Any final questions before we wrap it up for the week? Okay, all right, so that's all we got time for today. So this is the cutoff, and so after today, we're going to start something new on Monday, but that one's not going to be on the midterm. So today is the cutoff for midterm 2. Okay, so remember, check out the study guide for midterm 2 online. If you haven't chosen your final project group yet, please do so. If you don't do it by Friday, I'm going to do it for you. And you may not like the topic or the people that you're working with. So if you want to have choice in that, make sure you send me an email by Friday. All right, so thank you guys for coming today. I hope you guys enjoyed your weekend, and I will see you guys next week.
So I have another advice question.
Sure.
I think I talked to you the other week about like the 476B lab or whatever, how there were that many sections. How often do they take you off like the wait list? Because I'm like third or fourth on the wait list. Or, I don't know about labs because I know like they're stricter about labs than
Right.
like
Yeah. So for the labs, they're a little more strict because there's a certain number of space they can have in the lab.
Yeah,
And so part of it is going to be how willing the instructor is going to be in terms of like, having bigger groups. And that's ultimately what's going to boil down to. And so it's going to depend on the instructor. And it's going to depend on just how many students need to take 476B and how many sections we can actually offer. Because I know we're really struggling to find instructors for that one.
okay,
And so we may just ask instructors to just add more students to their section.
okay.
But yeah, it's a live situation. So
Oh, okay.
unfortunately, I wish I had better updates
So
for you.
it's okay.
That's kind of where it is.
Okay.
But we are going to try to make sure that everyone who needs it will be able to take it this semester.
Okay.
It's either going to be a combination of the sections getting bigger or just adding a new section. But we're figuring it out. But it'll happen before the end of the semester.
Okay.
Yeah.
Okay, thank you.
Yep.
But everyone averages, the average is like around 50%.
Well, like, yeah, exactly.
What does that mean?
Cole, Aniket, any final questions before I wrap it up? All right. See you guys next week.